Today we're going to be talking about a methodology called acceptance sampling, and this is a methodology that we can use to sort of make decisions about whether we should accept or reject batches or lots of material. So it's essentially a sort of a quality check. The key thing I want to focus on, though, is that we're going to be focusing on how we quantify risks of making wrong decisions and making sure that our sampling plans account for the risks of making errors, and specifically that we control the risks. So by way of an agenda, I'm going to start off just with a kind of a quick overview of what is acceptance sampling. And the majority of the webinar will be focusing on sampling for attribute data, which essentially means that each unit that we assess is either acceptable or not. It's a pass-fail result. Towards the end, we'll talk briefly about how to extend this methodology for variable type data. I also want to define what are called type 1 and type 2 errors. In this particular problem, sometimes we call them producer and consumer risks, and how we set those and why they're important to understand and control through the sampling plan that we end up calculating. The operating characteristic curve, or OC curve, is sort of an important function which really dictates how a given sampling plan will perform in terms of what kinds of quality levels will it routinely reject or accept, and where is there uncertainty. And essentially what we're doing is we're going to pick 2 points on that curve and fix them and identify the errors that we could make at those 2 levels of quality. And then from that, we'll learn how to develop a sampling plan that has an OC curve that goes through those 2 points, and therefore controls the risks that we could make of making wrong decisions when we sample units from production or incoming material. Towards the end of the webinar, I want to talk a little bit about some additional sampling plan metrics. So once you have a plan, we could look at things like what's the average quality that we should expect coming out of the sampling plan, and also get some idea of how much sampling we're going to end up doing depending on the actual quality level of our production. There's a type of sampling plan that involves taking more than 1 sample. It could be 2, which we call double, or it could be more than 2, which would be a multiple. Just briefly describe why you might look at those kinds of plans and what the pros and cons are. And like I said, at the end, we'll talk a little bit about sampling plans for variable type data. And I'll also give you my 2 cents on maybe some methods that are even more effective than acceptance sampling for ensuring that we're controlling quality adequately. Okay, so again, we've got, well, at this point, about 85 minutes. So I'll leave roughly 10 or so minutes at the end for questions. All right, so from an overview perspective, what is acceptance sampling? Essentially, I kind of view this as I don't really view it as a control procedure that's going to tightly control our process, and I'll explain more about why that is here soon, but it's really more of an audit or inspection procedure. Now, this could be done on incoming materials or incoming components. It could be done on outgoing finished goods at the part level or system level. So we get to define how we're going to apply sampling to what kinds of materials or products throughout the supply chain and throughout our value add steps in our own facility. And I'm going to focus on this webinar on sampling plans that allow us to objectively accept or reject, say, a batch based on a plan that was developed under the need to have certain statistical properties. Okay, I mentioned earlier in the intro that we're going to be focusing on attribute. So attribute and variable are really like the type of data. And generally, we have different statistical methods that are good at handling attribute data or categorical data, and then other methods for variable type data. And one thing that's pretty consistent is that when we're dealing with attribute data, we generally need more of it. We need larger sample sizes to kind of know what's going on or make decisions. Whereas variable type data, data is more useful to us because it's not just pass or fail. We know by how much a failure is or by how much a passing is. We get a quantitative assessment of that characteristic. And so one of the advantages of variable sampling plans that we'll see is that the sample sizes are going to be more reasonable. But just to be clear, so for attribute sampling plans, when we actually identify a sample size, it's going to mean that each unit that we look at as part of that sample will have to be assessed, and it's essentially the result for each assessment is either a pass or a fail. Okay, there's not going to be a dimension like of diameter or length or tensile strength that we're going to write down. It's either acceptable or it's not. Variable sampling plans, as we'll see later, we will record variable information about, leak rates or diameters or whatever we're measuring, and then calculate some statistics like means and standard deviations, and then use that data to determine, make a judgment about the entire batch or lot that we're trying to disposition. Now, the application for acceptance sampling can be several. I'm just really focusing on two here. Typically you might be in a production environment where you're either an incoming inspection or outgoing inspection before you ship. You're sampling units from those lots of material or lots of components, and just determining whether, based on the sample, we think the lot is reasonably good, that we should use it, or perhaps that it's not acceptable. If we end up satisfying the requirements to reject a lot, then typically you'd have a procedure as to what to do next. Either just outright reject it and return it to a supplier, if you're talking about incoming material, of course, maybe scrap or rework, or perhaps do some additional inspection. Now, on a process validation application of acceptance sampling, we're really trying to determine not to accept or reject a lot, but really to accept or reject the current state of the process and decide whether we can go ahead and move into production, full-scale production, given that the process seems to meet the quality requirements and is validated, or to reject that and to require that we figure out why the process does not appear to be meeting its quality targets, and then that would require some sort of improvement before we try this again. Now, while I'm not a big, really fan of acceptance sampling as far as tightly controlling quality, as opposed to 100% inspection, it's certainly more efficient, less costly to take samples and make decisions about the lot than to measure everything in the lot every time, right? A lot of times that's just not feasible, and especially is not even possible, say if the testing is destructive. Okay. Now, as I've mentioned a few times, whenever we make a decision based on the sample, and we're trying to make a decision not about the sample, but about the population or lot that it comes from, there's a risk that we make a mistake, and we call these producers' risk and consumers' risks, and I'll be defining these in more detail here shortly. So just to be clear, by sampling, you could think of a random sample, which is sort of randomly selecting units from some larger set of data. So for illustration here, we want to know something about the health of, say, fish in the Great Lakes. We might go ahead and collect some samples and look at their age and weight and evidence of disease and these kinds of things, and then make a decision or an inference about the population based on what we find in the sample. There are lots of other sampling strategies which we don't have time to get into here. One idea is to sample with stratification, where we sort of identify stratums in the data. It could just be physical location, like in a lot. We don't want to sample everything from one location. We want to stratify this into areas and sample uniformly, like randomly, but from different stratum. And that this is common in like voting polls, where you wouldn't you might split up the stratum by demographic and make sure we sample equally across those different ranges, since one demographic may be more likely to vote for one candidate versus another. All right, so what big part of this webinar is to learn how to come up and develop an appropriate acceptance sampling plan. So what does the plan consist of? Essentially, we're talking about defining the sample size, which we'll call N. That's how many units we want to look at from the larger population that we're trying to disposition. And then the actual objective criteria that we're going to set up ahead of time, which tells us whether we should accept or reject the larger population that sample comes from. So what is the criteria for acceptance? So that is the sampling plan. Now, as I mentioned at the beginning, there's a couple ways to do this. We're really focusing in this webinar on what's called a single sampling plan. So we're going to make our decision based on one sample, one random sample from, let's just say, the lot. Okay. There's other ways to do this, where you could plan for, let's say, the possibility of taking more than one sample. So in a double sampling plan, depending on what you see when you take your first sample, you may or may not require a second sample. Like if the results are not very conclusive in the first sample, you'll take an additional sample, not necessarily of the same size, and then base your decision as to accept or reject on the total results of both samples. And we'll come back to look at the double sampling plan towards the end of the talk. Okay, let's, because I'm going to be showing you some expressions, I want to just define some notation up front. So we're going to use capital N to indicate the lot size. And by saying lot, I'm talking about the unit, or I don't know, the population that we're trying to disposition. So we're going to, in this context going forward, we're going to be either rejecting lots or accepting lots. And a lot, is usually like a group of material that's produced, consecutively under certain conditions, similar conditions, based on, some one or more lots of raw materials or components. But we get to kind of define what a lot is. But the key thing is it's generally more homogeneous within a lot than between lots. Little n is going to be our sample size. So that's how many we're going to select from the lot in order to make a decision about acceptance or rejection of the lot. Now C is what's called the acceptance number. So the acceptance number is the maximum number of defective items that you're allowed to find in the sample that would still result in you accepting the lot. Okay, so anything more than C would lead you to reject the lot. C or fewer would be an acceptance. And then D is just the actual number of defective items in the lot. So one thing you could say about all four of these letters and what they represent is that they're all integers, right? They're all numbers, whole numbers, integer numbers between 1 and technically infinity. All right, so if we're sampling from the lot, and we're going to base our decision on a single sample, we would base the lot disposition based on this criteria, given the notation I just defined, if D is less than or equal to C, we're going to accept the lot. Remember, D is the number of defects we find. C is the maximum allowable that you can find and still pass the lot. On the other hand, if D is greater than C, if D exceeds the maximum number, then we have to reject the lot. So there's either one of these has to be true. Either D is going to be less than or equal to C, or it's going to be greater than C. There's nothing that's not covered here. And again, this is the making a decision based on a single sample from the lot. So just a couple of quick illustrations, pretty easy. Suppose our sampling plan were n equals 15 and c equals 0. So what does this mean? This means that you're going to, each time you get a lot that you want to disposition, you're going to take a sample size of 15 items or units. You'll assess them, and the acceptance number is 0. So this is, some people call it like a 0 allowance or 0 failure acceptance plan. If any defects are found out of the 15, then we have to reject the lot. Now what about one where n equals 60 and c equals 2? So with that plan, right, you would take the lot, you would take a random sample of 60 units, and then you'd begin to assess them. And let's suppose you got all through with all 60 and you've only found one defect, equals 1. Well, in that case, D, the actual number, is less than the maximum, so you would accept the lot. Even if D was equal to 2, you would accept the lot. But if, at any point during the assessing period when you reach D equals 3, right, you would reject the lot because 3 is going to be the minimum number that you would find. Okay, so that's sort of how the plans look and how we decide. Now, how do we actually get to these plans is going to be a big question in the webinar. I want to spend just a minute explaining what's sort of going on with this decision to accept or reject. It's actually considered what's called a hypothesis test. So in hypothesis testing, you have a statement that's called the null hypothesis. We write it H with a little 0 for null, or H0. And in hypothesis in acceptance sampling, it's standard that the null hypothesis is that the lot is acceptable. In other words, that's what we're going to assume to be true. So we're hypothesizing. Then there's an alternate hypothesis, H sub 1, that is, in this case, the lot is unacceptable, like it's not of sufficient quality. So the way this works is that we're always assuming the lots are good unless there's considerable or strong evidence to the contrary. So the way hypothesis testing works is not like, well, it seems like we're maybe 60% sure that the alternate's true. Let's reject the null hypothesis and include the alternate. No, we're looking for confidence levels more like 90 or 95%. So unless you're highly confident that the alternate is true, you're just going to go with the null hypothesis. This is why this methodology, I don't think, is a very rigorous control approach, because it's going to depend on the sample size, and we'll see this a little later, but just because we don't reject the lot does not really mean that it's a good lot. It just means that it's not bad enough that we are highly confident that we should reject it. Now, we are going to control risks on both sides, the risk that we accept a bad lot and we reject a good lot. So we're sort of going to be controlling for both errors. But in general, right, just because you don't reject a null hypothesis does not necessarily mean that this is actually true. An analogy is our criminal justice system, where, of course, the null hypothesis in that decision is that the accused is innocent, and the alternate is that the accused is guilty. And sure enough, in a criminal trial, it's required to have strong evidence by having 12 jurors all agree before you would reject the null hypothesis and conclude the alternate. Even if 1 out of 12 is unconvinced, then rejection doesn't happen. Might be a mistrial, but it won't be a conviction. All right, so let's look at this little thing called a truth table. And in general, like when you've got this null and alternate hypothesis, we have these 4 scenarios, right? We have the truth up here, and then our decision on this axis. So up in this upper left box, that's the situation where the null hypothesis is actually true, and our decision is to not reject. Our decisions for the null hypothesis, so we made the correct decision. And then down in the lower right, the truth is that the alternate hypothesis is true, and our decision is for the alternate. So again, we've made the correct, this time we've rejected the null hypothesis, but we've done so correctly. So this is where we want to be most of the time, but it's unrealistic to think we're always going to be there. So we need to think about what are the errors we could make and what are their probabilities. So what if the null hypothesis is actually true, yet my decision is for the alternate because I got some data and it led me to reject the null hypothesis. So if you do that, it's called a type 1 error, and the probability of making a type 1 error is something called alpha. So it's also called the significance level. This is related to the confidence level in rejection. So in other words, if we make a, we determine what alpha is. So if we determined, let's just say that alpha is 5%. Okay. Then that means what? That means that the chance that we're going to reject the null hypothesis incorrectly is 5%. So when we reject, chances are we're not in that 5%, we're in the rest, or the 95%. That's our confidence level in our rejection. So the confidence level is 1 minus alpha, or in this case, 95%. Okay? So by specifying your type 1 error probability, you're basically specifying the confidence level you have when you reject the null hypothesis. 95% of the time when we reject, we're going to be correct. 5% of the time, we're going to be incorrect. If we specify alpha as 10%, then we know 90% of the time when we reject, we're going to be correct, and 10% of the time we're going to be incorrect. So that's the type 1 error. Type 2 error occurs when the truth is the alternate, but our decision is to not reject the null hypothesis. Okay? It's called a type 2 error. It's a failure to reject when we should reject. And that one has a probability that we write as beta. This one is a little more complicated. This one is going to be highly dependent upon the sample size that we use when we make our decision. So as we're going to see, kind of the name of the game in acceptance of it is going to be to identify what sample size do we need given our alpha and given our desired beta so that we achieve probabilities of making errors that are reasonably, that we can tolerate. All right, so here is just a kind of summary of the risks. Now, type 1 error, in this context, we usually see it called the producer's risk. And this assumes that you're doing this as sampling on outgoing material. So if I reject a good lot, that's the risk I'm taking. It's like I'm going to incur the cost of not shipping something I could have shipped. On the other hand, type 2 error, it's the risk that I don't reject a bad lot. So it's a consumer's risk because there's a chance I'm going to send out a bad lot to my consumer, to my customer, or to the consumers, and they're going to get poor quality. So it's a risk there. Kind of I'm putting on the risk I'm putting on the consumer. Now keep in mind, the reason we have these risks is that we don't really know the true proportion in the lot unless we assess everything in the lot. we're trying to make a decision based on our sample, and we may get samples that are not really representative of the underlying lot. All right, so this is just this table relabeled. Instead of type 1 error, I'm showing producer's risk, and instead of type 2 error, I'm showing consumer's risk. Okay. All right, now I mentioned this OC curve at the beginning, and I want to talk a little bit about what it is. And I think I want to take you through how you would actually, given a sampling plan, how you would actually construct or generate the OC curve. And the reason I want to do that is it helps you understand something called the binomial distribution that we're actually going to be using to help calculate our sampling plan. Okay, so what the OC curve is, it's a plot. And on the y-axis is the probability that we're going to accept the lot, probability of acceptance. And on the x-axis is the sort of hypothetical true lot proportion defective. So again, we don't know what that is, but what we're saying is, let's suppose it was 0.5%, 1%, 2%, 3%. What's the chance we're going to accept the lot given that the underlying proportion defective are these different numbers? So here's an example of an OC curve for some sampling plan that we could just make up called, it says sample size is 60 and the acceptance number is 1. So again, just to review, what does this mean? This means that we're going to take a sample size of 60 from our lot, and as long as we observe 1 or fewer defects, 1 or 0, we'll accept the lot. If D is more than 1, as soon as we find 2 defectives, we're going to reject the lot. So given that's our sampling plan, the OC curve tells us for different lot proportion defective, now this is of the actual lot, not of my sample, what's the chance with this sampling plan that I'm going to accept the lot? Now it should make sense to you that as the lot proportion defective approaches 0, that the probability of acceptance is going to be like close to 1, almost 100% chance of acceptance. So probability go between 0 and 1, but if you multiply those by 100, you get percents. So this is really 100% or probability of 1. And then as the lot proportion defective gets high, like 10% effective, we're pretty close to having almost no chance of accepting that lot. And it's just going to approach 0. Now obviously in here somewhere, we're going to have pretty random results, right? So let me just go there for a minute. Suppose with this sampling plan, we were trying to, have this perfectly precise plan that would suggest that, okay, if the proportion effective of the lot is less than 2%, we'll let it go. We would like to let it go, just accept it. And if it's anything worse than 2%, we would like to reject it. So the question is, how will this particular plan perform? Well, if we go to the OC curve and look up 2%, out to the curve right across, we see that there's a probability of acceptance of about 66%. So the results are going to be not very, consistent from lot to lot. If all of our lots are at 2%, 66% of them will pass and 34% of them will reject. Okay? So this sampling plan is not going to be very effective at, at a single level of quality, accepting everything to the left and rejecting everything to the right. Yeah. So this plan can't really discriminate. In fact, what we've asked for is this ideal OC curve that essentially has like perfect acceptance up to our critical value, 2%, and then perfect rejection after that. So really, no plan is going to look like this. Now we can approach it by having very large sample sizes, which are not going to be realistic. But let's see how we do this. So this again, this ideal OC curve is not really going to be attainable. The slope of our OC curve will get steeper as the sample size goes up. As you can see on this picture, I took the OC curve that I just showed you, n equals 60, c equals 1, and then I left the proportions the same, but I doubled it, 120 and 2, 180 and I sort of tripled it, 180 and 3, and you would see like this is going to become more vertical around the ratio of 1 to 60 as we would just sort of kept increasing the sample size. Just as a side point, if we keep the sample size the same and we increase the acceptance number, that causes the OC curve to shift to the right, meaning that for a given proportion effective, or you can think of it as shifting up and to the right, as we increase for a given proportion effective, there's going to be a higher probability of acceptance if we allow 2 failures than if we only allow 1 failure. Okay, now what I want to do, this is probably maybe the trickiest part of the webinar, is I want to kind of go through how we would develop this OC curve from given some sampling plan. Now, in real life, you're not going to have to do this if you have a piece of software, right? You're going to, once you calculate a sampling plan based on your criteria, controlling the errors that we talked about, it'll give you the OC curve so you can sort of understand how it's going to perform, but I think it's going to be instructive just to kind of understand where this is coming from. So first of all, let me just state that this methodology that I'm going to use here has an assumption, has a requirement that our lot size is large relative to the sample size. And how large does that need to be? Well, we could go it the other way. The ratio of the sample size to the lot size should be less than 10%. So if our lot sizes are 1,000, okay, our sample size can't be more than 100, or this math starts to fall apart. We'd have to use a different function. So if this is true, then we can use what's called the binomial distribution to model the number of defective items that we are expected to find in a sample size of n, okay? And this distribution has 2 parameters, which is the sample size n and the proportion defective, the true proportion defective, which is p. Now, this will become easier to see when we have an example, but let me just restate this. This distribution, this is an attribute distribution, discrete distribution, calculates the probability that we would find exactly d defectives in the sample size of n, given some probability of finding a defect. You could also use this to find the probability that when we flip a coin 10 times, we get exactly, I don't know, d equals 3 heads out of 10 flips. In that case, n is our number of flips, 10. D is the number of heads. And p is the probability of getting heads on any given flip. That's 50% or 0.5. So if you plugged all this in, you could calculate the chance that you'd find 3 out of 10 heads. Let's take a look at an example of this. Suppose we take a random sample from a lot size of 10,000. And we know historically that probability of finding a defect is 3%, or 3% of the 10,000 are defective. What I want to know then is what's the probability of obtaining exactly some number of defective items, let's call it 4, out of a sample size of 150. Well, that's what the binomial tells us, right? So let's set that up. So I'm just going to take my original expression and plug in the numbers. So D was 4 defectives. The sample size was 150. Again, D is 4. N minus D, 150 minus 4. And P is the proportion effective. That's 3%. 1 minus p would be 1 minus 0.03 or 97%, and n minus d. Now, let me try to explain where this expression comes from. This part of the function gives me the probability that I would find 4 defective units, with each one having a probability of 3%. So I'm literally going to multiply 3% times 3% times 3% times 3% 4 times. Okay? Because when I'm trying to write out the total probability that I observe this sequence, it's literally the product of each of the individual probabilities of each item. So the first item has a probability of 3% defective, as is the second, as is the third, as is the 150th. So 4 of them are defective, so that's 3%. And then the rest, 150 minus 4, or 146, are not going to be defective. The probability of not being defective is 1 minus 3%, or 97%. All right, so this is the probability that I would find 4 defects with this probability and 146 good ones with this probability. Now, what is the left side? The left side accounts for all the different ways in which I could find 4 defects out of 150. It could be that the first 4 I sample are all defective and the rest are not. Or it could be the first one and the 7th one and the 8th one and the 150th one. Right? There are a lot of ways that you could order or like which units out of the 150 are actually defective, and that's what this part does. It's called a combination, and it's really n choose d. You may have seen this before. N choose d. That equals this thing here. So it's n factorial over d at the bottom, d factorial, also in the bottom, n minus d factorial. And hopefully you remember factorial, so this would be 150 times 149 times 148, all the way down to 1. So this is rather cumbersome to compute. Now you could do some canceling here, because 150 over 146 factorial, once you get to 146 factorial, those cancel. So anyway, but this is still a really large number. But when you multiply all this together, you end up with 19% roughly. So that means there's a 19% chance that you would find exactly 4 defectives out of 150 if the underlying proportion defective were 3%. Now, a faster way to get this is to use a function that's either in, statistical software like JMP or Minitab, or you could use Excel. Excel has a function which is the binom dist function, where the arguments here are d, the number of defects found, and the sample size, p, the proportion. And then you would use false as the last argument, which is a version of this function, which is an exact, probably finding exactly d, exactly 4 in this case. So if you go to Excel and type this in, you'll also get the 19.2%. Now, let's just extend this a bit. When we accept a lot, we said, well, we're going to accept a lot when d is not equal to c necessarily, but less than or equal to c. Number of defects is less than or equal to some maximum number. So we actually, if we're going to apply the binomial to calculate the probability that d is less than or equal to c, all we learned so far is how to find it when d is equal to some number, 4. Okay. So just by extending this, to compute the probability of acceptance, we're going to have to apply the binomial distribution starting at d equals 0, so d0 defects, d equals 1, d equals 2, all the way up to c. So we call that the cumulative binomial distribution. So basically we're going to sum up, this is a summation, starting at d equals 0, and stopping when d is at its maximum number that would still provide an acceptance. The rest is the same. So let's look at an example of this. It's just extending the last one. Suppose again, the lot size is 10,000. And notice the lot size doesn't come into this problem as long as the ratio of sample size to lot size is less than 10%. But anyway, again, the P is 3%, and we want to know what is the probability now that we find not exactly 4, but that we find 4 or fewer. So if C equals 4 represented the acceptance number, then we want to find the probability that we find 0 defects, 1 defect, 2 defects, 3 defects, or 4 defects. And so we'd be applying this binomial 4 separate times. The only thing that changes each time is the value of D. So first it's 0, then it's 1, then it's 2, then it's 3, then it's 4. We add all these up, and in this case it's 53.1%. Now again, I can use the binom dist function, and here instead of using false, if I change this to true, then you're telling Excel that this is a cumulative binomial distribution. You need to find the probability of up to 4, up to and including 4 out of 150. Okay, we're almost there. So everything we just did was with P equal to 3%, right? Everything that we just did with that cumulative binomial was with P equals 3%. But to get an OC curve, I need to look at how does the probability of acceptance depend on the actual P. I don't know what the proportion defective is on my lot. To do those calculations, I assumed it was 3%. But now I want to look at how does the probability of acceptance depend on the lot proportion defective. So I'll go back and redo this for different values of P, 0, 0.01, 0.02, or maybe even numbers in between, which I did here. And then I have, I can see how does the probability of acceptance change as the lot proportion defective starts at 0 and increases. That's the OC curve, right? This is the relationship. This is on the x-axis. This is on the y-axis. So there's my OC curve. So I've gone through how could you start with some sampling plan and then derive the OC curve, which will say, based on this criteria and this, this acceptance number and this sample size, how will this plan perform in terms of, leading to acceptance given the lot proportion defective. Of course, it's going to start near 1 for low proportion defective and near 0 for high proportion. But where it falls off is going to depend on the sampling plan. Okay. Now, keep in mind that what I just went through using the binomial distribution, that only applies when we're doing what we call sample with replacement, which is assumed to hold when the ratio of sample size to lot size is less than 10%. Sample with replacement kind of means that when you find a defect, it doesn't really change the underlying chance that you'll find another defect. If your lot size is very large, then finding one, doesn't mean that you're not going to find another one. It's kind of like flipping a coin as well. That's perfect replacement, right? The probability of a heads on the second flip in no way depends on what you got on the first flip, okay, when you're just looking at that point in time. Now, if you violate this, let's say you're dealing with small lot sizes of 20 units and you're sampling 3 or 4, well now you're greater than 10%. So you would need to use a distribution called the hypergeometric distribution to set up this plan. This handles the changing probabilities of finding defects as you find them. That's called sampling without replacement. And again, the software will generally handle that if you need to. All right, so let's look at how we design the sampling plan. I'm going to set this up and show you how you would do it mathematically. We won't solve it because it's kind of complicated, but then we'll move into looking at some software examples. All right, so we want to design a sampling plan to achieve some OC curve that we just learned how to generate, where I'm going to control the risks at 2 points along the OC curve. And those points we call the acceptable quality level, AQL, and then the rejectable quality level, RQL. Okay, so let's just define these. The AQL, I mean, it says acceptable, so it kind of gives it away. It's a level of quality, and when by quality, we're talking about proportioned effective. It's a quality level that is, I hate to say it's acceptable, it just doesn't sound right, but it's small enough that we're okay with passing lots of this level of quality. Obviously, we're not talking about like defects that are, could cause injuries or deaths. We're talking about being more cosmetic or defects that may cause the product to stop, but it's not going to be safety critical. So it's a quality level where we expect that there's a high probability of accepting the lot at that quality level. Something like 90 or 95% chance it will accept. Then the RQL is kind of like the other end. It's the sort of the maximum proportion effective you would ever want to tolerate on an individual lot, and only because you made an error. We want our sampling plan to be designed so that there's a very low probability of acceptance at that level of quality, at that higher proportion effective level. Now, obviously, we have to think about how we're going to choose AQL and RQL and the risks associated with them, the risks of making errors. The levels themselves are going to depend on risk, right? Ideally, we'd like 0 defects, 0 proportion, but these have to be 2 different proportions. One which we're going to say is, we'll tolerate, and one that is, we don't want to accept. Now, the levels themselves will also depend on where you're deploying this methodology. If you're doing process validation activities, your quality levels are usually going to be lower than if you're doing a production sampling plan, where you've already validated the process, and the smaller these levels are, and the lower the risks, the larger the sample sizes are going to be. So at some point, you're going to run into a cost issue or feasibility issue in production if you try to get too low on these. But in validation, the last thing we want to do is put a process that's not validated to be capable of meeting a certain quality level, into production. So we want to make sure that we bite the bullet and do what's ever required to validate that for that phase. All right, and as it says here, for process validation, very often we set RQL based on the criticality of the defect. So if it's a critical defect, RQL is going to be much lower than if it's maybe something like visually. All right, so let's finish this off here. I'm going to sort of show you how to set up the calculation of how would we get the sample size and criteria so that we're controlling risks that are AQL and RQL. So just to make the equations look a little easier, I don't want 3 letters, I just want like a P with a subscript. So I'm going to define the acceptable quality level as P sub 1 and the rejectable quality level as P sub 2. And now I want to think about, so I'm really going to need 2 equations because I need to calculate N, the sample size, and C, the acceptance number. Those are my unknowns. That's what makes up the sampling plan, as we talked about at the beginning. So I want to write down 2 statements that reflect the probability of acceptance, number 1 at the AQL and number 2 at the RQL. So at the AQL, right, what should we be doing? We should be accepting at that better level of quality. So the probability of acceptance is going to be something like, I don't know, let's just say 95%. So my error that I would make is to reject. So that we said was alpha. Probably that I reject the null hypothesis correctly is alpha. So if that's my error probability, then the probability that I accept at the AQL is going to be 1 minus alpha, 1 minus the chance that I incorrectly reject. That's going to be the left-hand side of my first equation. So that's a probability of acceptance at the AQL. Probability of acceptance at the RQL, right? At the RQL, what do we want to have happen? We want to be rejecting So accepting is an error. That is beta, consumer's risk. Okay. Now, we know in general, this is the expression we have, right? Probability that D is less than or equal to C, that leads to acceptance, is this cumulative binomial. Now we're going to write this twice, once at the AQL, once at the RQL. So at the AQL, that's P1 now. So we just said at the AQL, probability acceptance is 1 minus alpha. And then we just have our cumulative binomial distribution from D to C. The value with P1 is equal to the quality level associated with the AQL. And then at the RQL, we have beta here. Probability of accepting at the RQL is an error. That's beta error, consumer's risk. And this is at P2. All right, so what do we have here? We're going to specify P1 and P2. Right? We have to define what those are. We also need to specify alpha and beta. What risks can we tolerate? Now what's left? We have D, C, and N. Now D isn't something we really need to solve for here. It's just a counter. It starts at 0 and ends at C, and it just shows up here, but it's 0 defects, 1 defects, 2 defects up to C. So it's just going to be used in the calculation, but it's not a constant. It's just a counter here. C and N are the constants we need. Now we have these two equations, and so we have two equations and two unknowns, N and C, like once we identify what P1 and P2 and alpha and beta are. So we could solve these two equations for the two unknowns. Now it's not as easy as solving two equations in algebra where you just, solve for one and plug it into the other, or can't find a way to cancel terms. This is more of an algorithm where we have to search for the values of N and C that allow alpha and beta to be no higher than the values, the constraints we put on. So it's more of a numerical procedure, which we won't do by hand, obviously. All right, let's look at an example then. We want to design a sampling plan given we've defined AQL, RQL as 1 and 5% respectively, and then my producer risk is 5% and my consumer risk is 10%. I'm not suggesting these are good numbers or bad numbers. They're just illustrations at this point. So I'm just kind of showing you where I'm specifying this in a package called Minitab, creating a sampling plan. This is like an attribute for attributes. The units here are proportion effective, so I'm putting in 0.01 and 0.05 for the AQL and the RQL. And then I'm putting in my alpha and beta, my producer and consumer's risks of 5% and 10%. I'm going to leave the lot size blank for now. We really don't need it to get the sampling plan. It's and you'd only be using this if you know your lot sample sizes are going to be less than 10% of your lot sizes. So when you click on OK, it kind of just summarizes what your inputs were. And then here's the plan. Sample size N is equal to 132, and the acceptance number is equal to 3. By the way, you can solve these equations in Excel using goal-seek function. Not done that, you can set that up without too much difficulty. So you can have Excel solve this for you. So again, this says what this is. Accept a lot if defective items in 132 is less than or equal to 3, otherwise reject. And now it doesn't, these have to be integers. So the actual probabilities are going to be very close to what you specified. In other words, the errors at 1%, there's a little less than a 5% chance will incorrectly reject a good lot that's at 1%. And there's a little less than 10% chance that we'll accept a bad lot that's at running at 5%. Okay, so these are the criteria we put in. And then this is the OC curve that results from this particular acceptance plan. And we covered how you would generate this just given the N and the C using the binomial distribution. What we did is we we kind of worked backwards, right? We calculated N and C by doing what? By fixing, let me go to the next slide, by fixing this point and this point. Okay, so at 1%, which is the AQL, we said that this curve can drop no more than to 95%. Probability acceptance has to be at least 95% at the AQL. And then we also said at 5%, which is the RQL, 5% effective, this probability acceptance can be no more than 10%. So these are the constraints that we imposed on those series of equations, and then we iterated these numbers to find like a plan that would produce an OC curve that goes through this point and this point. Now, one thing I think just to mention is I find that I think this is not really well understood. This is the plan. Now, what happens when you start using the plan? Let's suppose we take a sample and we reject the lot. What do we know? Like at that confidence level. Let me go back to this picture. If we reject, it's our attempting to think, oh, we must be at 5% effective because that's the rejectable quality level and we're rejected. Not really. What we could say if we reject is that we're, in this case, 95% confident that we're worse than the AQL. Right? Like if you're in here, you're accepting and rejecting, you might as well flip a coin, right? Like if you're at 2.5%, flip a coin. So if you're rejecting, you don't really know, are you here, 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 here? You know that you're worse with high confidence than you're worse than 1%, because if you were better, you probably wouldn't be rejecting. There's only a 5% chance of rejecting. And similarly, if you don't reject, it doesn't mean that you're confident that you're at the AQL. It means that you're highly confident that you're no worse than the RQL. Because if you were worse than the RQL, there's only a 10% chance you would accept that lot. So, don't get excited just because you put a sampling plan and you pass the first few lots. Yeah, it doesn't mean you're as good as the AQL. Okay, that's what these statements are here. Yeah, there's not much informative on this slide other than just kind of showing, again, what happens to the OC curve as you increase the sample size while leaving the acceptance number 0, you're basically kind of dropping this curve down and getting a little steeper. So you're sort of reducing the area where you have a lot of uncertainty between acceptance and rejection, where your probability of acceptance is kind of close to 50%. Now, one issue you may have already realized, like some of these sample sizes we're talking about are kind of large. So you might say, well, I can't look at 130 units. I mean, that's ridiculous. So what can we do to reduce the sample size without, we can't just say, well, we'll accept 50% errors. I mean, that's not what we can do. But we could increase the RQL. So this distance between the AQL and the RQL plays a big role in the sample size that we need. If they get very close to each other, like I want the AQL to be 1% and the RQL to be 1.5%, good luck with that. You're going to need a really large sample size. So here I'm showing for this problem we just had, AQL of 1% with risks, producer and consumer risk, same as we just went through. What happens as I increase the RQL? So this was the one we just did. We got 132. Now, if I allow the RQL to go up to 10%, my sampling plan changed from 132 except on 3 to 52 except on 2. It's less than almost a third of the cost. And if I keep going, right, if I go up to 30%, then I only have to look at 12 units. again, if I accept this plan, it just means I'm no worse than 30%. So you have a more affordable plan, but you don't know as much. All right, so that's essentially how we set up these, calculate these attribute sampling plans. Okay, so in the 20 minutes I have left, I'd like to kind of quickly go through a couple of other ideas. So there are a couple of these other metrics that you could look at. The one's called average outgoing quality, and one is average total inspection. I'm just going to briefly kind of run through this. So essentially, these help provide additional information about your sampling plan, and you could also use this to help determine the final sampling plan. What the AOQ, or average outgoing quality, is it's you know, you can think of the quality level before you sample, and then the quality level after you're done with your sampling. And the reason why that would be different is it's assumed that if you reject a lot, this assumes that you're going to rectify the lots that were rejected. In other words, you're going to go through 100% sampling and either rework and fix everything or replace defective units with good units. So your lots that were rejected are going to be shipped with 100% good product. All right, so this average outgoing quality, it can be different than the incoming quality. Should be better. Now, how do you calculate this? I'm not going to run through where this expression comes from, but it's basically the probability of acceptance, okay? The underlying true proportion defective coming into the process, lot size minus sample size over lot size. Okay, so I've defined it here. Let's look at an example. Suppose our lot size, now to calculate these two metrics, you need the lot size. Suppose the lot size is 5,000. My sample size is 50. My acceptance number is 2. And my proportion defective in the lot is 1%. What's the average outgoing quality? Well, we can look at this a couple different ways. One is, for this actual lot, what's the outgoing quality? And then we can look at more generally, what if we allow P to vary? What would be the average outgoing quality for a range of defect levels for this particular sampling plan? Now, to calculate PA using the formula that I just gave you, just back here, we first need to actually calculate this, the probability of acceptance. That's just using the binomial distribution. So it's going to be binom dist, probability we find 2 or fewer out of 50, that's here, 2, 50, given that the proportion defective is 1%, true is accumulative, so that's 98%, 98.62%. So that goes here. And then we add P here, big N minus little n over big N, multiply all that together. You can see that your average outgoing quality is a little bit better than the incoming quality. It was 1%, and going out, it's, of course, rounding to 1%, but really 0.976%. What if we wanted to generate this AOQ like a curve, AOQ versus P? You would just repeat this for different values of P, just like we did when we generated the OC curve. In fact, Minitab will give you this plot. So the one we just did was 1%. That was like right here. It's just below the 1%. Now you can see here, we happen to pick a point in our example that didn't really change the quality much. But imagine we were using this sampling plan on lots that, I don't know, had around 4% effective. We would be rejecting more lots. Looked at the OC curve, we'd see that we'd have more lots rejected, and we'd fix all those lots, right? So we'd rectify them. So actually, the outgoing quality level is much, much better than 4%. It's around 2.5%. Okay, 2.5% reflects defects that got through on lots that we accepted, okay, that presumably had some defects in them. So one thing that sometimes people look at is say, what's the worst case for this sampling plan? In other words, what's my this is the average outgoing quality versus incoming proportion defective, but what's the limit? It's the maximum of this curve. Okay, so this suggests that, like, about worst case, going out the quality going out of my facility is no worse than 2.6%. regardless of what P is. Out here, we're rejecting more and more lots, and we're rectifying them, so the actual outgoing quality is going to be much better. It's just going to come at a huge cost. Down here, the quality level is really good, so we're not going to be rejecting many lots, so not a lot of difference between the incoming and the outgoing. The other metric you could look at is just a sort of a measure of the total inspection cost. Again, it's going to be a function of the lot size and the sample size, and we can take a look at this. Average total inspection, it's on average, how much of each lot are you going to be inspecting? Okay. Again, I'm not going to explain where the formula comes from, but it also requires you to calculate the probability of acceptance. And with the same example I had before, same data, we can calculate that, plug it in, and in this case, the ATI comes out to be 118. So let's just think about that. The lot size is 5,000, sample size is 50. So if we were going to reject every lot, then our average inspection would be 5,000. We'd have to look at everything in the lot. If we rejected no lots, then we'd only be inspecting the sample sizes, which would be 50. So we're somewhere in between the 50 and 5,000. And then you could look at that, just like we did before, you could vary the actual proportion defective and see how does the inspection cost vary depending on that average total inspection. So again, for lots that are like perfect, if there are no defects in this process, our average inspection is going to be at 50, which is where this pops out, just our sample size. That's our average, will be our sample size. If we're rejecting all the lots because they're running at 20% effective, then we're going to be up here at average of 5,000 per lot, which is everything. So depending on your proportion, you can get an idea of what on average, how many units per lot are we going to be inspecting. So for a given sampling plan, you have your OC curve, you could get your AOQ, and then your ATI curves. All of these are a function of the sampling plan. These two depend on the lot size as well. The OC curve does not. Okay. Let me say a few words about the double sampling plan. Again, still talking about attribute data. This is where we may require a second sample to disposition the lot. Again, dependent upon the results of the first sample. So for the notation, I'm just going to add an extra N and C for the second sample. So we have N1, C1, the sample size and acceptance number for the first sample. And then N2 and C2 are the sample size for the second sample, and C2 would be the acceptance number considering both samples. So the way this works is I have like a little process flow and then an example following. You inspect, you start your sampling and you have your N1, which is your first sample, or the first sample size for the first sample. And then you check them all, and then you record your D1, the number of defects observed in the first sample. If your number of defects found is less than your acceptance number, the maximum allowable, then you're done. You accept the lot. And if it's worse than C2, which is the acceptance number for both samples, and it's so bad that you reject right away. But if your D1 is somewhere between the acceptance number for C1 and the acceptance number for C2, then you go to another sample. You actually collect N2. And then we compare the combined number of defects on both to C2 and decide to either accept or reject based on is it less than or equal to C2 or greater than C2. So here's an example where you start with 40 and your acceptance number is 1 on the first sample. Okay. So if you're 1 or less on the first sample, you're good, you're done. If you're more than 1, then we look at the second C2. And so if we were worse than 3, like if we had 4 in the first sample, again, we're done. We reject right away. If our D1 is, 2 or 3, right, bigger than 1 but less than or equal to 3, then we'd have to take a second sample and then compare the sum of the defects in both to this cutoff of 3 to decide whether to accept or reject. Now, you could generate an OC curve for some double sampling plan. I've done it once. It's sort of tedious because when you calculate the probability of acceptance, you have to consider that you could accept on the first sample or you could accept on the second sample, and you have to add these probabilities together. It's a little bit tedious to add up. Now, there has to be some advantage of doing this to overcome all the complexity. The only advantage in a double sampling plan is that you can reduce the cost of sampling versus a single sampling plan while still having the same risks of rejecting good lot and accepting a bad lot. Can do that at the cost of some more complexity, especially if in general you don't have any problems, but once in a while you encounter a process change that causes a problem or a bad set of raw material. This may be advantageous. The disadvantages of the double sampling, if you're not using curtailment, where once you reject a lot, you just stop, then this might actually be worse in terms of cost. And obviously, it's going to be more difficult to implement and track everything. Some of you may have come across the acceptance sampling plans through some standards that have been published. There's a military standard and a commercial standard, ANSI standard, which deal with defining acceptance sampling plans for attributes. I've used these a little bit, but some of the problems I have them is it's sort of like difficult to know which table that you actually should use. You're not calculating a sample size based on controlling AQL and RQL and the risks at both ends. A lot of these are based just at one end, like the AQL. You're really only controlling the AQL. There's also different levels of kind of sort of inspection levels, if you will, where as you start to reject, if you reject a lot, you're going to move to a more stringent inspection level where you may need a larger sample size, say. And then there are rules for switching between normal to tightened or from tightened back to normal and then from normal to reduced. And then the plans are also organized by lot size and also these levels of inspection. So you sort of can, what I find is there's so many choices that you can kind of decide, well, this is the most I can afford, so I'll just go with this one, rather than doing what's right as far as controlling the risks. The last thing I want to cover briefly is a few words on acceptance sampling for variable data. So this is, not feasible when your inspection results and you like looking at the part and seeing is there any visual color issue or distortion, or it would be if you could actually measure like deviation from target or something with the equipment, but essentially if you're actually measuring like a dimension or something, you could use acceptance sampling for variables. Now what you're going to do is you're still going to take a sample, but instead of counting number of defects, you're going to take a sample and calculate like a mean and a standard deviation, like the statistics that let you quantify the variation. And one unfortunate thing is that these plans tend to assume that the data is normally distributed, which clearly is not always going to be the case. And if it's not normally distributed and you assume it is, then your risks are not going to be what you think they are. So what you do is you calculate the mean and the standard deviation, and then you sort of compare how far, in terms of number of standard deviations, the mean of your distribution is to the spec limits. So mean minus lower spec divided by standard deviation, upper spec minus mean divided by standard deviation. These are called z-values. They tell us specifically how many standard deviations the mean is above the lower spec, and how many standard deviations the upper spec is above the mean. And then there's also what's called the maximum standard deviation, which is if your standard deviation is above this number, you can forget like passing any lots, because it doesn't really matter where your process is located on a two-sided problem, because even if you were a nominal, standard deviation is too large. Even if your process is perfectly centered, standard deviation is too large to meet the quality objectives of your plan. So here's an example. The AQL is 0.02% and the RQL is 1%. Producer risk and consumer risk I have both as 5%. And in this plan, you can assume, if you want, you can assume the standard deviation is known. I'll show you that in a minute. Here, I'm not assuming that. And then here are the spec limits. So you'll need the spec limits in this problem as well. So I'm just basically putting all this stuff in, and then calculating a plan which says, okay, so take a sample size of 39. The critical K, which is the number of standard deviations you need to be, your mean needs to be away from spec limits, should be at least 2.93. And here's the maximum standard deviation. So to pass, it says it down here, you have to calculate these z-values that we talked about here a minute ago and make sure that they exceed 2.93 on both the lower and the upper. Then you're going to accept the lot, assuming that you don't exceed the maximum standard deviation, your z lower is bigger than k, and your z upper is bigger than k. That means, like, you know, if your curve is real tight in here, then your spec limit is many standard deviations away from the mean. So things look really good versus the curve has more variation and your spec limit's not enough standard deviations away. So just like with the attribute plan, you can have an OC curve generated. Okay. And then what this plot kind of shows you, it's called the acceptance region plot. So if you were centered between the spec limits, what were the spec limits here? 0.475 and 0.5. So 0.5 is nominal. That's the most your standard deviation could be. As your process average is shifted toward a mean, your standard deviation allowable is even less. So this is sort of the feasible kind of acceptance region of that plot. Now, one thing that sometimes people will do is they'll sort of pretend that they know the standard deviation. Right? Either whatever it is they estimate, or they'll just base it off a long-term known value, and you put it in. And now all that variation is uncertainty, standard deviation is sort of eliminated. And as a result, you can greatly reduce the sample size. I mean, we went from 39 down to 8. Okay, now you'd have to have some justification for assuming you know the standard deviation, and maybe you have to be monitoring that like on a control chart to justify that. Advantages of variable plans are, of course, we can get smaller sample sizes and also deal with smaller AQLs and RQLs. Trying to do that with attribute plans would be quite expensive in terms of the sample size needed. Things to watch out for acceptance sampling for variables are these methods assume data is normally distributed. Okay? Often not the case. So they kind of fall apart for non-normal data. And then, to the extent that you have different specs and different standard deviations, you sort of have to have different plans for different characteristics that you're monitoring, different variable characteristics. Bottom line, and I'll end with this, is that, if you've already got variable data, perhaps we should just be doing some statistical process control, especially on the inputs to the process, and try to get out of the inspection acceptance sampling game. So just to kind of finish this, acceptance sampling, as I said at the beginning, it's more like an audit tool. It's not a direct stringent process control technique like SPC would be. I'm very much a proponent of kind of trying to do less inspection and more process control by figuring out what in the process upstream needs to remain stable and within what ranges, and using some SPC techniques to ensure that we're monitoring that and reacting more quickly. Of course, part of that is then assessing, once we're stable, that we have a proper capability, but at that point forward, monitor the process performance over time.